Welcome to our explanation of how self-driving cars see the road. Self-driving cars, also known as autonomous vehicles, use a combination of sensors, cameras, and sophisticated software to navigate roads without human intervention. These vehicles are equipped with various sensors like cameras, radar, and LIDAR to perceive their environment. These vehicles are designed to perceive their environment similar to how humans do, but using technology instead of eyes and a brain. In this video, we'll break down the complex systems that allow these cars to see and understand their surroundings in simple terms. Sensors continuously collect data about the car's surroundings, detecting obstacles, road conditions, and other vehicles. This data is processed by sophisticated software that helps the car navigate safely through its environment. The key components of self-driving systems include various sensors, processing systems, navigation software, and control mechanisms. In the next section, we'll take a closer look at the cameras that serve as the eyes of self-driving vehicles. Self-driving cars use multiple high-resolution cameras positioned strategically around the vehicle. These cameras function like human eyes, constantly capturing images of the surroundings from different angles. Cameras can detect multiple elements essential for navigation, including lane markings, traffic signs, traffic lights, other vehicles, pedestrians, and obstacles. Advanced systems use stereo cameras that work together to create depth perception, similar to how our two eyes help us judge distances. The system compares the images from both cameras to determine how far away objects are, creating a three-dimensional view of the environment. While cameras are effective in daylight conditions, they have significant limitations in poor visibility. Heavy rain can blur the camera lens and distort images. Fog reduces contrast and obscures distant objects. At night or in darkness, cameras need additional lighting or must be supplemented by other sensor technologies. These limitations are why self-driving cars rely on multiple types of sensors working together. In summary, cameras serve as the primary visual sensors for self-driving cars, but they're just one part of a complex sensory system. Radar systems allow self-driving cars to see in conditions where cameras struggle. Radar, which stands for radio detection and ranging, works by emitting radio waves that bounce off objects and return to the sensor. The radar sensor emits radio waves that travel outward. When these waves hit an object like another vehicle, they bounce back to the sensor. Unlike cameras, radar systems can detect objects and measure their distance, speed, and direction even in poor visibility conditions. Let's compare how radar performs against cameras in various weather conditions. Self-driving cars typically use multiple radar systems with different ranges for various driving scenarios. The vehicle's computer processes this radar data alongside information from other sensors, creating a comprehensive understanding of the surrounding environment and enabling safe navigation in all conditions. LIDAR, which stands for light detection and ranging, is a critical technology for self-driving cars. It works by shooting out millions of laser pulses per second and measuring how long they take to reflect back after hitting objects. These measurements create a three-dimensional point cloud, providing a detailed map of the car's surroundings with incredible precision. LIDAR can detect the shape and size of various objects around the vehicle, helping to identify whether something is a pedestrian, cyclist, car, or stationary object. While LIDAR works well in most lighting conditions, its performance can be affected by heavy precipitation like rain or snow. Self-driving cars need powerful computer hardware to process the massive amounts of data collected by sensors. These specialized computers process terabytes of data every hour from cameras, radar, LIDAR, and ultrasonic sensors. Complex algorithms fuse data from all these different sensors, creating a unified understanding of the environment. This sensor fusion compensates for the limitations of individual sensors. For example, if cameras are blinded by sunlight, the system can rely more heavily on radar and LIDAR. By combining data from multiple sensor types, the car's brain maintains a complete picture of its surroundings, even when some sensors face challenges. Computer vision is critical for self-driving cars to understand their surroundings. Computer vision starts with analyzing raw visual data from cameras mounted on the vehicle. The system first extracts features from the image, detecting edges, colors, and patterns. Next, it identifies regions that might contain objects, creating bounding boxes around them. Then, each detected object is classified with a confidence score, determining what it is. Computer vision in self-driving cars leverages deep neural networks trained on millions of images. These networks learn to recognize patterns and features that define different object categories. Beyond detection, self-driving cars must predict how objects will behave. For example, the system needs to differentiate between a parked car, which will remain stationary, and a car waiting at a traffic light, which might move soon. Similarly, it needs to predict the movement of pedestrians to ensure safety. All this object detection and prediction happens in real time as the car moves. The system processes dozens of frames every second, tracking objects as they move around the vehicle. This constant visual analysis allows the self-driving car to understand its environment and make informed decisions. To summarize, computer vision helps self-driving cars detect and classify objects, predict their behavior, and process all this information in real time. This visual understanding is essential for enabling safe navigation through complex traffic environments. Self-driving cars need to know exactly where they are on the road at all times. They use a technique called SLAM, simultaneous localization and mapping, to create maps while tracking their position. The SLAM process works by sensing the environment and detecting landmarks. As the vehicle moves, it continuously updates its map of the environment. Many autonomous vehicles also use pre-mapped areas with highly detailed information. These maps contain road layouts, traffic signs, and landmarks with centimeter-level precision. By comparing sensor data with these precise maps, self-driving cars can achieve centimeter-level accuracy, much better than standard GPS. This precision is essential for safe navigation, lane keeping, and obstacle avoidance. This precise localization and mapping capability is what allows self-driving cars to navigate safely in complex environments. After a self-driving car understands its surroundings and location, it must decide what actions to take. Path planning algorithms calculate the safest and most efficient route to reach the destination. These algorithms consider multiple factors and evaluate different possible paths. The system predicts the future movements of other road users by analyzing their trajectories and behaviors. This prediction includes a measure of uncertainty, as other drivers may change their behavior. Control systems translate the path planning decisions into actual driving commands. These include throttle, braking, and steering instructions that control the vehicle's movements. These control decisions are made dozens of times per second, allowing the car to quickly react to changing conditions. When an obstacle is detected, the system immediately adjusts its plan. Self-driving cars operate on a continuous decision-making cycle. This includes perception, localization, prediction, planning, and control, all happening in milliseconds. This complex decision-making system enables self-driving cars to navigate safely through traffic, following rules while adapting to unexpected situations. Modern self-driving systems use machine learning to continuously improve their performance. Companies collect driving data from their entire fleet of vehicles, which helps train more advanced algorithms. When one car encounters a new situation and handles it correctly, that knowledge can be shared with all other vehicles in the network. This is similar to how human drivers gain experience over time, but at a much larger scale. Let's compare how human drivers learn versus how a self-driving fleet learns collectively. This collective learning helps self-driving cars become increasingly capable of handling complex and unusual road situations safely. The continuous learning process creates a powerful feedback loop where the entire fleet benefits from each vehicle's experiences, making self-driving systems increasingly capable and safe.